Today, natural resource sectors face increasing pressure from population growth, market demand, and climate impact. Agriculture needs to produce more food with fewer inputs, forests need to be managed sustainably, and the energy sector must transition to cleaner sources while remaining economically viable. Meeting these challenges requires a balance, economic, environmental, and social. GIS helps create that balance by providing a geographical lens to understand where resources exist, how they are changing, and what actions will produce the best long-term results. Throughout this module, we will explore how organizations across agriculture, forestry, mining, and renewable energy use GIS not only to improve operations, but to support sustainable and regenerative resource management. By the end of this module, the goal is to understand natural resource management as a balance of three interconnected dimensions: economic value, environmental protection, and social well-being. When one dimension progresses at the expense of the others, systems become fragile and unsustainable, which highlights the need for long-term, holistic planning rather than isolated interventions. We will explore how the four-step GIS workflow, visualize, understand, plan, act, applies to natural resource operations. The emphasis is not just on collecting data, but on transforming observations into meaningful spatial understanding and ultimately into informed, actionable decisions. Monitoring tells us what is changing, understanding explains why those changes occur and how future scenarios may unfold. Throughout the module, we will look at how diverse datasets, satellite imagery, field observations, climate models, biodiversity records, and land use data can be integrated within GIS. This integration supports resilience across different domains, from agricultural productivity and forest health to watershed management and ecosystem restoration. Ultimately, GIS is positioned not simply as a mapping tool, but as a transparent analytical framework that reveals spatial relationships, clarifies trade-offs, and guides strategic decisions. When used this way, GIS becomes a foundation for sustainable, evidence-based natural resource governance. Sustainability balance. Achieving long-term sustainability requires balancing environmental protection, economic viability, and social well-being without advancing one at the expense of the others. Natural resource resilience. The capacity of natural systems to absorb stress, adapt to changing conditions, and recover their function after environmental or human-driven disruptions. Regenerative resource management. A management approach that not only minimizes harm but actively restores ecosystems, rebuilds soil and water systems, and increases long-term natural capital, spatial understanding, insight. Gaining explanatory insight by analyzing spatial relationships, revealing why patterns occur, what drives change, and where interventions will have the highest impact. Natural resource management sits at the intersection of economic profitability, environmental protection, and social well-being. Progress is only sustainable when these three dimensions are balanced, not when one advances at the expense of the others. This is where GIS becomes more than a mapping tool. It provides a framework to translate raw observations into spatial understanding and ultimately into informed, location-aware action. Most natural resource workflows follow a clear progression: visualize data to establish a shared picture of conditions, understand spatial relationships, patterns, and drivers plan operational strategies. Based on these insights, act confidently with field applications and decision systems. This progression, from fragmented data to coordinated, evidence-based action, is what enables resilient and regenerative resource management. As global populations and economic demands rise, pressure on natural systems continues to intensify. We extract more water, more timber, more land, and more minerals than ever before. The problem is that many ecosystems cannot regenerate at the pace we consume them. When extraction exceeds natural renewal, soil degrades, forests diminish, watersheds erode, and biodiversity declines. Monitoring plays a decisive role here. It helps us detect change early, identify trends, and understand where systems are reaching their limits. With timely insights, decision-makers can intervene before degradation becomes irreversible. Without monitoring, we only realize we've crossed the threshold when the damage is already irreversible. Sustainability is not only about protecting nature, it's about balancing three interconnected priorities: environmental health, economic value, and social well-being. If decisions optimize one dimension at the expense of the others, systems eventually fail. For example, Agricultural expansion may boost short-term productivity, but degrade soil and increase drought risk if unmanaged. GIS supports sustainability by providing spatial evidence that connects these three pillars. It allows us to see where development can continue responsibly, where ecosystems need protection, and where communities are most vulnerable. When we monitor natural systems, we learn what is changing: a drop in vegetation cover, reduced crop yield, rising sediment in a watershed. But observation alone doesn't tell us why these changes occur. Understanding begins when we combine datasets, satellite imagery, land cover maps, hydrology layers, biodiversity surveys, into a spatial context. GIS helps us connect the dots: how soil type influences drought sensitivity, how land use expansion fragments habitat, or how elevation and temperature shifts affect species migration. With this deeper understanding, we move from reacting to symptoms to addressing root causes. This allows resource managers not only to document environmental stress, but to forecast future scenarios, test interventions, and prioritize action where it will have the most impact. Now that we've established this foundation, let's take a look at how this understanding translates into real-world practice. What can we achieve with GIS in agriculture, forestry, water systems, and ecosystem management? A lot of organizations stop at monitoring. They download satellite images, generate NDVI maps, write reports. And that's it. But in this series we went one decisive step further. We moved to understanding. Why does that single step change everything? Monitoring simply tells you something is changing. Understanding tells you why it's changing and where it's heading. Monitoring gives you early warnings, hundreds of them. Understanding separates the real emergencies from natural fluctuations. Monitoring creates mountains of data. Understanding distills that mountain into insights you can actually act on. And most importantly, monitoring alone keeps you forever reactive. Understanding turns you proactive. And even predictive. Bottom line, observation makes you aware of the problem. Understanding makes you ready to solve it. To understand what's happening in the field, we start by monitoring crops and soil conditions. Satellite imagery and indices like NDVI help us detect stress before it impacts yield. At the same time, soil moisture and nutrient data guide irrigation and fertilizer use precisely where needed, reducing waste. Field teams collect observations with mobile apps and IoT sensors, creating a shared, real-time picture of conditions across the entire farm. This gives us earlier insight and more accurate, targeted interventions. Result: less water, fewer inputs, and reduced losses, yet higher yields and healthier soils. Monitoring is used not only to view the status but also to drive decisions. Digital field twins allow us to proactively plan operations by bringing together satellite imagery, weather data, cost, yield, and regulatory data into a single system. By digital field, we are referring to the creation of a constantly updated virtual copy of the real field. This enables precision agriculture applications to increase yield while reducing input usage and mitigating environmental pressure. GIS, Geographic Information Systems, also helps us monitor regenerative agriculture practices such as cover cropping, carbon sequestration, soil health, and minimum tillage. As a result, agriculture becomes not only more efficient but also more resilient and sustainable in the long term. Forests change continuously due to climate pressures, land use, and ecological processes. With satellite imagery, LiDAR, and field observations, we can monitor canopy conditions, biomass levels, and habitat quality at scale. These data layers help detect early warning signs such as disease spread, wildfire susceptibility, or illegal activities. GIS also enables understanding of forests as connected ecosystems, mapping corridors that support biodiversity, identifying fragmented habitats, and highlighting areas needing restoration. Shared dashboards unify agencies and researchers around the same baseline data, ensuring ecological monitoring is transparent and actionable. Monitoring provides the raw observation. However, for understanding, change must be interpreted temporally. Change can be quantitatively analyzed by comparing multi-temporal datasets, layers such as annual canopy loss, historical fire perimeters, and drought indices. Spatial analysis helps us separate the causes triggering this change. Is the problem climate-driven, a result of human impact, or due to past fire regimes? These insights reveal the resilience thresholds of ecosystems and where areas can recover on their own. Within this framework, GIS, Geographic Information Systems, is not a management tool. It provides a transparent analytical foundation that informs scientific decisions. In summary, GIS is not a management robot here. It acts like a mirror that offers scientific transparency and enables decision makers to see the best option. Healthy watersheds support ecosystems, agriculture, and communities by regulating flow, replenishing soils, and reducing flood risk. When forests are cleared, soils degrade, or urban areas expand without planning, hydrologic balance shifts, leading to increased runoff, erosion, drought vulnerability, and degraded water quality. With GIS, we can monitor how water moves across landscapes, from mountain headwaters to floodplains and urban drainage systems. Remote sensing, IoT hydrology sensors, and terrain models allow us to track runoff patterns, stream flow changes, groundwater recharge, and sediment movement. These insights help us understand how climate stress, land use change, and infrastructure affect watershed function. By integrating land cover data, soil moisture models, precipitation forecasts, and river networks, GIS reveals where conditions are shifting and where interventions like wetland restoration or green infrastructure are needed. Rather than reacting to damage after storms or droughts, this approach helps practitioners anticipate hydrological stress and guide more resilient water management decisions. Beyond tracking conditions, spatial analysis helps us understand risk. By modeling stormwater pathways, floodplains, and downstream dependencies, GIS allows us to see where water will move, not just where it is now. Hydrologic models reveal vulnerabilities, which neighborhoods flood first, which wetlands buffer runoff, or where recharge capacity is declining. These insights inform science-based restoration, resilient infrastructure decisions, and long-term water planning, but without prescribing specific actions. GIS provides the analytical foundation that supports coordination between environmental agencies, water utilities, and local governments. Ecosystems are dynamic systems shaped by climate, land use, and biological interactions. GIS allows us to continuously monitor ecosystem health using multi-source inputs, such as satellite imagery, Landsat, Sentinel-2, biodiversity records, field sensors, and climate layers. By tracking variables like vegetation vigor, surface temperature, erosion hotspots, habitat fragmentation, and species distribution, we can spot early indicators of stress before they escalate into irreversible decline. Temporal analysis is especially powerful here. Long-term imagery helps reveal trends that aren't visible in single snapshots. Monitoring doesn't just show what is changing, it establishes a data foundation for understanding why those changes occur and where intervention is needed. After collecting the monitoring data, the next step is to analyze what these patterns mean. GIS, Geographic Information Systems, allows us to uncover spatial relationships, showing how agricultural expansion affects habitat corridors, how rising temperatures lead to tree mortality, or how urbanization alters the nutrition of wetlands. By integrating climate scenarios, species distribution models, and land use projections, we can determine which ecosystems are most vulnerable and in which areas restoration would be most effective. This analysis phase is what transforms our observations from a dry report into vibrant, actionable strategies. Let's bring these core ideas together. We began with the GIS workflow: visualize, understand, plan, act, which gives us a structured path from raw observations to informed, coordinated action. Without this workflow, data remains fragmented. With it, we can move confidently toward solutions. But technical workflows alone aren't enough. Sustainable resource management depends on balancing three dimensions at once: economic value, environmental protection, and social well-being. If one advances at the cost of the others, the system becomes unstable. This is why we distinguish monitoring from understanding. Monitoring tells us what is changing in crops, forests, water systems, and ecosystems. Understanding explains why it is changing, what the drivers are, and where the trend is heading. To reach that level of insight, GIS integrates multiple data sources: satellite imagery, field sensors, climate layers, land use maps, and turns them into spatial understanding. It transforms scattered information into something we can analyze, compare, and act upon. And across all sectors, agriculture, forestry, water, and ecosystems, GIS acts as more than a map. It becomes an analytical mirror, revealing trade-offs clearly, showing where limits are being approached, and helping decision makers choose the most sustainable path forward.